Good morning, everybody. Zoom was giving me a hard time to get started today. Technology sometimes doesn't want to cooperate. But anyway, today we're going to talk about, speaking of technology, we'll talk about a topic that I really like, latent variable mixture modeling. So if you recall, a latent variable is an unobserved variable. And when we were doing latent growth curve modeling, when we were doing confirmatory factor analysis, structural equation modeling, exploratory factor analysis, we were discussing latent variables as variables are that underlie observed variables. So in essence, they are the reasons why things happen to the observed variables. Like for instance, in a survey, a latent variable, say representing something like positive affect would result in one scoring high on items reflecting positive affect. I feel great about myself. If I have this underlying sense of positive affectivity, I would tend to score higher on unmeasured measures of positive affect. Okay, so that's what we learned about latent variables. And we also learned that latent variables, regardless of the type of measured variable, are continuous in nature. That's what we learned. However, we can take this a step further now and create what are known as categorical latent variables. Yes, we can do that too. And these latent variables are designed to identify different different hidden classes of individuals based on whatever variables we're measuring, right? So let's let's delve into this some more. Excuse me. So this is a method that helps us identify the number of unknown classes, right? Based on a set of dependent variables. I'm going to get into everything and clarify everything as we move along, okay? So this method seeks to identify the number of these latent classes in a set of data. And these are defined by some measure of separation, right? So if you imagine you have groups of people, if the groups of people just form one group, everybody's intermingling, that then we say, okay, there's one group of people. But if you imagine the groups of people starting to separate into cliques, we could say, oh, well, there's that one group and that there's another group. And that's what we're trying to identify. So question is, how far apart do these folks have to be in order to be considered different, right? So the further apart they are in multivariate space, and multivariate because we're generally dealing with more than one dependent variable, right? The more likely they are to represent distinct classes. So our goal is to find some separation between these classes so we can say, hey, they are actually distinct classes. Again, going back to the metaphor where we have people, right? Or cliques, right? We know there are things that distinguish cliques. And if we can imagine that this distinction, like maybe clothing, etc., is somehow quantifiable. So we can say, wow, those people are really, really different. Like the emo people are really, really different than the preppy type people. So, how do we know they're different? Well, there's got to be some measure that represents the distance between the two. And the in general, the two measures that we use to identify the um, the optimal number of classes that have, that are well separated are the Bayesian information criterion, or the BIC. You may remember Bayesian stats from us using Bayes' theorem for calculating positive predictive value. That's the same Bayes, right? And lower values of BIC are better. And then other criteria that we use are substantive criteria. And this is related to our knowledge of the field we're studying. So we can say, wow, these actually are distinct classes. So again, just like EFA, there's a little bit of I don't know, subjectivity in here, right? I would think it's not subjectivity, because if you have people who have knowledge of a field, they'd probably be better at, identifying distinct classes. Okay. Yeah. So we can use the BIC. One of the things we don't use is the likelihood ratio test because, or the chi-square test, right? Like we do with say CFA and structural equation modeling, because these models with different classes are not nested within one another. So that's why we use the BIC as our measure, as a our way of defining the how many different classes there are. Okay. So these classes are defined on some set of variables. So here's some examples. Example one, how many different classes are there representing body mass index? There could be low, moderate, and high BMI. So this would be an example where we have just like, say if we have one variable only, a univariate example, and we want to see how many classes there are, we probably can find some separation. I mean, you probably don't need to do latent variable mixture modeling for this because you have one variable and you can kind of just almost partition them based on knowledge, right? Another example would be how many different developmental trajectories, growth forms, are there representing change in smoking across 4 years? This is a little bit, more interesting because we might find that, because when we talk, so now this is when we're talking about trajectories, we're talking about a multivariate analysis here because we're going to have, say, smoking represented across 4 years, so year one, year two, year three, year four, and then you'll have these unique trajectories, something that we did in latent growth curve modeling where we defined this average trajectory, right? And we looked at the individual trajectories. Well, now we're saying, okay, well, maybe we can find hidden classes within this one, average trajectory where you might have individuals who are never smokers. That probably, being the majority would be in there, right? They'd have a class of their own. Then you'd have those who adopted early, so they started smoking early, and they're going to do whatever they do. And then you'll have these that that are late adopters that are kind of going to increase over time. Okay. Once we identify the number of latent classes, we can assess the factors differentiating the latent classes. And this is really what makes this method interesting. So again, we seek to identify how many latent classes there are, how many hidden classes there are in some set of data. But then the next interesting question would be how do we characterize these? And this is extremely useful. Like if we take the example of cigarette smoking, or let's say vaping now, okay? If we take the example of vaping because that's more common, or even just nicotine use, because overall nicotine, there's a lot of use of nicotine, but using different modalities now. If we could classify membership to these different latent classes, we can use this information to inform prevention initiatives, right? So there's a lot we can do with this. And the way we end up identifying these classes is using something known as multinomial logistic regression. So logistic regression is a type of regression that in which the dependent variable, the outcome variable, is categorical in nature. So it's a discrete categorical variable, right? And multinomial logistic regression is the type of regression that when there's more than two levels to the outcome variable, and we like to compare each level of the outcome variable to some comparison level. So if we're looking at, say, never smokers, early adopters, one of the things we'd like to do is like to compare late adopters versus never smokers, early adopters versus never smokers. That's something we do in multinomial logistic regression. Okay. So I'm going to step back before we get to actual data analysis for a second to the idea of a latent variable, a latent categorical variable. So these are, again, variables that we don't know about, right? Their existence. And we can kind of hypothesize them and say, well, there's probably this many classes underlying here. But we're not really sure, and we're going to let the data help us identify them, right? This is contrasted to a known group analysis. Like say if I divide data into males and females, right? I have males and females. Those are known classifications. That's a known classification. Or I could divide data into class standing, freshman, sophomore, junior, senior. Again, that's a known grouping, right? So this is an unknown grouping. Now we can have a mix of both. You can have both the known group and an unknown grouping and create something even more fantastic. Any of this stuff is possible. Anything is plausible when you're dealing with latent variable mixture modeling. And it doesn't have to be something that we see change over time, like my example of cigarette smoking or vaping across 4 time points. It doesn't have to be that. It could be just a cross-sectional analysis. I could throw a bunch of uh, a bunch of variables into the mix and then see how many classes emerge. I mean, if I just do one variable, so if you're doing one variable, it's almost not that interesting. I mean, it is a little bit, but it's almost not that interesting because you can do low, moderate, high BMI. I mean, you can almost infer those. There's going to be a high BMI, there's going to be a moderate BMI, and there's going to be low. The question is like, where's that cutoff? And this would help you identify that cutoff, but this isn't just the only way you could do that. Uh, it's more interesting when we have multiple dependent variables. So like let's say I was looking at a measure of health and one of the variables was BMI, another variable was blood pressure, another variable was water consumption. I don't know, whatever you want in there. You have all these variables and now you try to find latent classes. So that seems to be a little bit more interesting way to do this. But this is a great method. Some people also think of this as a profiling method. What? Because once we identify the classes, we can profile them. Now, the way we do this in M, and we're going to use Mplus here, is to do it all in one model, right? Both identify the number of classes and then also do the multinomial logistic regression. However, you can also do it a different way. Do look at the you can look at the number of classes and then create those classes and then do the multinomial logistic regression. Like you say, you do this in Mplus, and then you save the data on the classes, then you import it as SAS, and then you run the multinomial logistic regression. I know that Benk Muthain, who's the I guess the creator, him and his wife created this software. They've discussed that issue before, and they said that that eliminates the latent nature of mixture modeling because now you've created these variables and they're fixed, right? All of a sudden these classes become fixed if you take them out of the framework. However, I think this is the original way mixture modeling was done was to do it separately. And I don't see that as a problem because if you think about it, you can generate the number of classes, right? They're still latent. Now we're just going to go ahead and make a prediction. Whether it's all done in the same program or in 2 different programs, to me doesn't take away the fact that these were latent and then you've discovered them using this method, right? And so it's up to you how you choose to do that. I've done both ways. All right, so let's go into a couple of Mplus examples. So again, I asked you all to download Mplus. And your downloadable free version of Mplus allows you to have 6 dependent variables. So I have to be very careful what I do, but 6 is plenty for what we're doing here. 6 dependent variables. So I'm just going to go over the coding. And so I'll also, of course, do this in Mplus. So this is the Mplus code, and it's very small here. I don't know how to increase the size of this. I'm not that savvy, to be honest. Let's see, is there a way? Yeah. You know what? Sorry. I'm on a really large computer screen here. But so this is just the code here, and I'm going to go and break it down for you, okay? And what I'm going to do first is just run a crude model without any predictors, okay? And then we're gonna play around with this a little bit since we got some time to do that. All right, first step, as usual, is to have a data statement where are my data, and they're located in this file here. Now this is a long line, and you're allowed 90 characters. So I had to break it up. Like, see, I broke this down. This would normally be 1 line, but it's too long. Sometimes it'll work even with that case, but sometimes not. Okay, next thing I do is list the variables in our data set. So, our variables, and then we start with the names are, and then we name them. They have to be no longer than 8 characters long, and you can't have any spaces. So here I have not Hispanic with a little underscore. was going to sensation, but obviously I'm running out of room, so I just put Satan. Uh, Anxiety, angst, that works out well. And then you have to press 1, 2, 3, 4. Okay. And smoke 1, 2, 3, 4. We use semicolons at the end of all of these lines. We define our missing values as 9999 in this case. I mean, you can do whatever you want with them, but it's usually an impossible value. Now, I'll start by proposing how many classes I believe there are. So generally, I start with 2. And then what I'll do is I'll keep on adding classes and seeing how many we can have. And in some cases, you can have a lot, but then it becomes, after a while, it becomes almost implausible. You don't want to have really small classes. I mean, if you're talking about 5% of the data, that's really too small for it to be replicable, right? With future studies. So I don't like to go very low. Like I think there's some heuristic of 10% per no class should represent less than 10% of all the data. So you have to be careful with that because it's hard to replicate studies when you have these very small classes. These are the variables in my model. So this is the class statement is different from what we've seen so far. We didn't have that in any of the Mplus code we've run so far. The user variables, well, in this analysis right now, I'm just using depression 1 through depression 4, right? Because I'm just doing a crude model without any other covariates, if you will. And we add an analysis command, which we didn't always add. We did it when we ran the mediation model using Mplus to tell how many bootstraps we wanted. But here we're going to use the analysis model, and we're saying we're doing a type equals mixture. Now then I'm going to ask it to basically this is how many times I want to run and then optimize my models, right? So I'm going to run like 100 models, right? So I'm going to run 100 models and then I'm going to optimize them 10 times. So we're basically trying to reduce to compute the maximum likelihood estimate, the likelihood that we can replicate the observed data with our model. But this is 110, so this is very small, right? I should probably, if I was doing this I wanted to publish it, I'd probably do like 10,000, something like that, at least 10,000 starts and then 10 or more replicate optimizations, right? So, but I'm just for our case, I'm going to do 100 here and 10. All right. Following the model command, we start with identifying our population. So this is our overall population. So you have to have this percentage sign, overall percentage sign, right? And then this is my population model. It's a linear model. So this is your latent growth curve model, right? Linear model with depression at time 0, 1, 2, 3. We already talked about this last week with latent growth curve modeling. Then I'm also going to ask for a plot because I'm going to be able to visualize this. Hopefully this will work here. I want a plot of my data. And then I'd say plot type equals plot 3. So this is a type of plot where what I'm looking for is a line that's based on the means. And so I'm basically telling it to do that here with this line. The series is depression 1 through 4, right? And then I'm going to use for output, I'm just going to ask for standardized results and confidence intervals. Okay, so let's try this. Make sure this works out well. All right, let's go to Mplus. So that's the code I have here. Sorry, again, it's small, it's hard to see. All right, so let's run it. So what I did was I had to change. Well, one thing is I'm using comma separated values, and that's something that Mplus can deal with. So I don't have to convert it to something very, very specific. One thing that you'll notice is you can see the computations happening, and I love that. It's so cool. Until it gets maximized. We have 1,837 cases. Let's look at number of missing data patterns, or 11 missing data patterns. So we have some missing data. So this is showing how much missing data there's a time point. I mean, how much complete data we have a time point for. We have like 89% of all values. Time point one, we have 96. And going from time point one to time point two, we have 91, and so on. This just shows you what these are. These are. And here you can see the log likelihoods, right? And how they're changing. Well, actually, they're stable. So that's why, we can stop here, right? And these are the seed values. You have to start by entering a number like a seed. Let's feed this in. This is where I want you to start. So what we're dealing is with this, with four variables. We're dealing with a four-dimensional space, right? And we're trying to find where the maximum likelihood is in that space. And, the thing is, if you just do a 100 like I did here, with 10 optimizations, you're not looking over that whole space, right? Because that space can vary. Now, be as abstract as you can. Imagine there's these hills everywhere, and you think you're at the peak, but there might be another peak somewhere that you didn't even look at, right? So that's why you do these different seed values. And we can enter our own seed. And then once we find like the optimal one, we can, if we're worried about replicating these findings, I could just save that seed and say, just start over here, I'll replicate that finding, right? So that's pretty cool. It says here the best log likelihood value has been replicated, rerun with at least twice the random starts to check that for the best. So saying, hey, do twice, random starts. So do 200 instead of 100. Right. So you can do that again. And it's going to give me that if I do 200. So it's just saying you should run as many as possible to make sure that this is the best possible result. Okay, so it gives me this likelihood value, which I'm not as interested in because I'm not really doing anything within that model, within that class where I can actually do a nested model. I could, right? Obviously, you could do that if you wanted to, but I'm really interested in the Bayesian information criterion or criteria, and it's look at this value. The value itself means nothing, right? It only means something when I'm comparing it to other values, other models, right? But by in and of itself, this doesn't say anything about how well the model fits the data. Truthfully, what I would have done first is, since I'm using a growth curve model here as my data, right? I did a linear model of depression across those 4 time points. I would first run a latent growth curve model and see how well it fits the data. So I would have done that separately before I started this process. Okay. So let's see what kind of stuff it gives me here. Well, it gives me this final class counts and proportions for the latent class based on the estimated model. So actually so it just gives me what the counts are, right? So like say like there's 276 folks, you can pick and choose, but I like the final class counts of proportions for latent classes based on the most likely latent class membership. So I use this one, 1561 in class 1 and 276 in class 2. So this is already a small amount of people, right? It's like 15% of the people. Now, it doesn't mean that we wouldn't have more classes. We can try that in a second. Entropy gives me this value telling me how good the separation is among the classes, and the higher values are better, and they range from 0 to 1. We can also look at this. These are known as posterior probabilities. This is basically what the Bayes theorem does. When you're regular stats class, this is actually using that, right? You have information on the individuals, and then we're going to test what their class membership is based on that individual, on knowledge that we have. That's why it's called posterior probability. And we want the diagonal values to be as close to 1 as possible. And these aren't that bad. Some people say above 0.8, some people say above 0.9. So this looks okay, decent. That's actually using Bayes' equation. And then, I want to look at the model itself. So within each class, what do we have? So we look at in class 1, this is that really large class, right? Our average for depression at baseline is 15.635. So this is a 639. This is a measure using the Center for Epidemiological Depression, CESD. It's a depression scale. Depression, CES, Center for Epidemiological Studies Depression Scale, right? So CESD. And this was its baseline level. It's like 15.639, and it ranges somewhere from 0 all the way up to 60. So that's, it doesn't seem very high, but this is reasonably high. These are adolescents. So that's that group. And then that smaller group, we'll look at their values. Their means are a lot higher, like 31 point, right? So these kids have way higher depressive symptoms. It's very interesting, right? The intercept value is significant, but there's no change from baseline, so they stay depressed. And here we have same thing. Their lower depression and their rate of change or their slope is not significant, so they stay less depressed over time. Okay, so that's how we start this. I'm not looking at this other stuff yet because this is just step one. So let's do something for fun here. So I think I have an Excel document I can use. Let's just create one. A blank document. Let's play around with this, okay? Let's just call this classes. Yes. And we did a 2-class model, do a 3-class model, and let's look at the BIC. And we'll add these other things like entropy, although you're not supposed to use entropy as a way to identify classes, right? All right, so let's just play with these for a little bit here. Let's say class counts. Uh, Smallest class. Let's do smallest class, right? Small, right? Smallest class. Because usually that's the one we're concerned about. That's not too small. So in the 2-class model, we had a big. Big was here. Okay. Put that in here. Control B. I think our entropy was, what was it, 0.79 or something like that. Entropy was 0.7, yeah, 0.789. Why? Yeah, sorry. Why are all the other numbers afraid of 7? Because 7, 8, 9. I can't help it. Every time I see that, I'm sorry. 0.789. And our smallest class was 270, 15, let's say 15%, okay, 0.15%. That's what I'm concerned about. 0.15. That's 2 classes. Yeah, okay, cool. And if you want, you can do something like the seed. We had a really nice seed here. If we need to replicate this exact model, we can just look up that seed. Planting seeds. Okay. It seems like all of these work, but just have one of them in there. Control V. All right, there you go. Let's do 3 classes to see what happens. This is fun, huh? I think this is really fun. I mean, you say, well, because we don't know, right? I mean, we kind of know that there's going to be people who are depressed and not, but right now that one depressed group has really, really high scores. I wasn't thinking about that. So let's go to the next one. Let's add 3 classes. 3rd class. There's so many other things we can do with this, but let's add the 3rd class. Let's run that. I love seeing that work. Looks like I'm doing all this cool stuff. 1837, of course, that's going to stay the same. It still says best log likelihood value has been replicated. Again, we would want to run double and many more. So here's an interesting thing. Let's see. So I ran 3 classes and I basically have the same 2, but now I have this tiny class with only 10 individuals. So that I wouldn't go with that because this represents like 1% of the data, less than 1% of the data to me. Even though all these other things are really nice, entropy is nice, the average, the posterior probabilities are all pretty high. I still wouldn't go with that because I only have 10 people in this class. So what does that tell me? It's very, very small class. We can look at it anyway, just for the fun of it. Let's take a look at this. This class, your mean of depression is really, really low, but it's increasing over time. But not, that's okay because it's so well. Actually, It's not even significantly different from zero at the intercept. So there's some growth, but this is like a very, very non-depressive. They could be people who just fill this out randomly, just put like low values. So it could be something like that. And then the 16, and then the last one, class two, sorry, class two is 15. And then class three is, yeah, it's basically the same as what we had before. So there isn't really much change. You'll notice one thing though, that the variances for the slope and intercept are constrained to be equal across classes. We could actually relax that and see what happens. So a lot of times you'll do that. Let me just show you what it would look like if we relax these. And then sometimes that'll cause problems, right? That'll cause problems in the model. Like what if I wanted to relax the intercept variance? I just do I. Really, that's all. So it's saying estimate that intercept variance. I could do I and S and just have them estimated. I don't think I need S for these. I think this is fine, but let's see. Now this could cause a lot of issues. And in some models, it'll slow it down a great deal because you have to do a lot more work. So let's see if we cause problems. No, no problem. But let's see what the outcome is. So it doesn't really change that much, even with the relaxed variances, to make sure it worked, actually, the relaxing of the variances. Maybe it didn't work. Mean variance 16, did it not work? Oh, it didn't work. Okay, so maybe I need to put the, let's try that again. It's been a while since I've done this, so I'm not so sure if it's even working. So it might not be working. Oh, I know what, never mind. I know why that happened. That's my mistake, actually. That is my mistake. I remember. So the coding is a coding issue. I think I would have to go, I'd have to actually do this in different classes. It's just doing the same thing because it's estimating it overall. I'd have to actually separate it for class one, something like, I think like something like this. I may not have this right. Class number one. And then the class, let me see if this works. Number two, this is cool, trying to remember all this stuff, right? And then we'll say, let's estimate them separately in class number two. And we've class number three. Dude, if this works, this would be awesome. My memory's not at a loss yet, right? Let's see if this works. Not 100% sure. Let's see. I might have wrong code. I might have to look it up. Let's see. Can be, see, it's already telling me it's working because you get errors right away. So it's telling us there's an error somewhere. But interesting. See how everything changed, right? The class counts changed because I did the release. The entropy went down a lot. These values are lower, right? Posterior probabilities, but there was something wrong with one of the variances somewhere. So well, look at the variances here. They're negative for class one, not negative for class two, not negative for class three. Let's go back to our class one variances. They were negative, and one of them is significant. So you can play around with that, right? And say, well, should I be releasing variances in all three of them and all one of them? But see, this is going to change the model, and there's so much that you want to do if you're going to test this model, right? To see if it's the ideal model. But let's not release the variances for a second and go back to this original. This is fine because I'm not doing anything different here, right? So I'm just saying that all the classes still are retaining the same model of the population. So let's run this again. And let's just fill in our table. Right? So we had our BIC values here. Let's go back and fill in our table. BIC. And our entropy value, if you recall, I think it was better, right? It was better, wasn't it? Yeah, 0.854. Now, in this example, everything's working really quickly, but imagine if we're doing it and it's not working very quickly. I think it was 0.0.01 was the class size. And then that seed was, what was the seed that we used? See how it changed, right? And then it stabilized itself right here. It went higher, right? Went higher, less negative. All right, so let's go here and all right. And we can actually start naming these models. So insert, model. So model one, model two, and then you can say stuff like this, variance, variance is fixed. Right, so we still fix, and we can do more. So you can do a lot of this is basically the process that you go through. You got to, it's very thorough and it's time consuming. Again, if the model is running slowly and you're using several thousand replications, it could take for a long time, like a day or something to run. But that's what you do, right? So I mean, if you have a really complicated model, this isn't a very complicated model. Okay, so let's well, let's look at the BIC actually decreased, so that's good. But if we use if we use some kind of substantive criteria, we could say, well, that last group that had less than 1% of people basically had a zero intercept. And even though it had rate of change from baseline, it only represented 10 people. My feeling is that this is like some kind of an irrelevant group. It could be one that's based on mistakes or people who just like didn't take their time to fill out the date the the surveys and the first, particularly at baseline, they're probably not paying attention. Maybe they started paying attention later, but it really messed everything up. So I'm not gonna use that. So I'll stick with this two-class model. Okay, so let's go back to the two-class model, right? So even though the BIC suggests we move down, we go to three-class model. Entropy is really nice, but this class is too small here. It's way smaller than, say, 10%. Even if I set it at 10%, minimum of 10%. And again, this is with the fixed variances. I didn't release the variances. So we could have played around with that for forever. All right, so let's go back with this two-class model. And now we're going to add some predictor variables, see what happens. Okay, so what did I say here? Okie dokie. Predicting class membership of depression on sex, where one is male and zero is female, and lunch, where one is receives a free or low-cost lunch, and zero does not receive any assistance. Okay, let's try that now and see what happens. This is where it gets even more interesting. Once we start adding the predictors, I mentioned we could have just taken these out and then taken these out of Mplus and put them into something like SAS to run the regression here. And there's only two classes, so now this is not multinomial logistic regression, really. It's binary because there's only two classes. If there were more than two classes, we'd say, okay, well, this is multinomial, right? All right, so let's go back and run these with predictor variables. Yeah, so we'll go back here. Let's close this since I already have this, say, close. Let's open I think I have it saved, crude model, this one right here, okay. All right, so now I'm going to add predictor variables. So I'm going to predict class membership, that's what I have to see, on sex. One is male, zero is female, and lunch, right? I also had to add those to my user variables. And none of the dependent variables are categorical, so I don't have that categorical statement like I did. And we will do that on our next session. We'll add categorical variables to this. We'll do with categorical variables. All right, well, let's run this. Now, there's several things I can do here, right? There's a lot of things. Like one, I could have obviously relaxed the constraints on the intercept and slope variance. That's one thing I could have done. The other thing I could do is, well, let's start by doing this first, and I'll show you what else I could have done. I won't scoop myself. All right, so I think we still have 1837. Isn't that what we started with? It was 1837. I think so, yeah. And let's go down to our models, okay? Pretty much the same. There's some changes now that we added the predictor variables in there in terms of the numbers. Everything else looks pretty good, like pretty much the same as what we had before. All right, so group one and group two, still pretty much the same. But what we're interested in is here. What's the effect of these predictors on the categorical latent variable? So we're saying we're sex and lunch. We're looking what's the effect of sex and lunch on being in class one versus class two, right? Right. And then, this is a logistic regression, so this is a log odds. But we can tell from that sex has a significant effect. This means nothing to us otherwise. And then lunch, where this p-value is not significant. Okay, that's fine. So we look at it in terms of odds ratios because that makes more sense to us, right? And we know that group one is the low depression and group two is the higher depression, right? Was that right? Let me see, make sure. Class one, class one had lower depression, 15, and class two had higher depression. All right, let me go back and look at the values again because I have to remember what they are. Male was 1 and female is 0. Okay. So let's go back here to the output and see what it says. Male is 1 and female is 0. Yeah, this is interesting. So this is with, I'm wondering if I have that code backwards because it's so counterintuitive from what we know about well, actually, maybe not. We'll see. Usually females have higher self-reported depression than males, but this is also a longitudinal analysis, and we're looking at these classifications because what these results are telling me here is that, and looking at the odds ratios, that males are, well, 1 minus 0.15 are 80, basically 85% less likely to be in class one than in class two. When we think of males usually having lower self-reported depression than females. So this could be, if this coding is right, then this could be a very interesting finding, right? School lunch has no impact on this at all. And this just shows you the reverse. So in this case, males would be 88% more likely to be in group two, class two than class one. That would be an intriguing finding, wouldn't it? Right? All right, so let's see what can we do here? So this is one way to test the model. This is just looking at the predictors predicting class membership and nothing more, right? A wise person may say, well, how do we know that there isn't a unique effect within each of these classes, right? This won't test that, right? This is just testing how we characterize those two classes. But if I want to do just a regular LGCM, right, I can do that. I can do IS on sex and lunch. What's next? Lunch. So this is going to look at what's the impact of these variables on the intercept and slope within the classes. Now, if I just do this, it'll do it with the same results within both classes, but it may have an impact, okay? Right, so what I'm saying here is then this effect will remain constant across the two classes. I can relax that as well, which I may do. So let's try this. Actually, before I do that, let's look at these results again. And let's enter some data into our table. So here's our BIC. This model 3. 2 classes, our BIC. All right. Interesting. Did I get the right thing? It's true. I'm making sure I have the right results. They might be the wrong results. Just make sure I didn't mess up. Oh, that's a 3 class model. That's fine. I thought, wait a minute, that's the results we just had. Here it is. Okay. BIC was that value. The smallest class was 18%, right? Fixed covariates. I'll call them external or internal. How's that? That sounds cool, right? I'm doing them within classes. Internal. Okay. And let's add the entropy here. So you see, this is a slow process, right? This isn't like I'm just going to get the answer and go home and have a beer. It's going to take a little while. And even with this is just an example with a very simplified example. Still taking time. And if you want to save that, you can do that as well. So let's go fill this table out. Why am I doing this? Because, hey, if I'm publishing this, I'm going to need these data, right? Not necessarily the seed, but everything else. Okay, so we're going back to 2 now. All right. Let's run our. No, this is the one we did here on 2. All right, so let's run model 4 with 2. So now we're going to run it with the within class regressions. So let's go ahead and do that. All right, this is it. Yeah, this is it right here. All right, let's run. I think we actually ran it, but I'm just running it again. We'll run it again. The rate takes a little bit longer. Tiny bit longer. Everything else is good. Here again, it's telling me to run it again and again and again. All right, so some things has anything changed? BIC 48092. Is that better actually? Let's see. If it's not better, then I'm not going to use it. It has to be better. I see it's getting better. And my entropy was what? Navigating this stuff is pretty wild. 0.803 and 14%, 0.803 and 14%. 14% is the size of the proportion of the data in my smallest class size. And I said the entropy was, what did I say it was? Entropy was 0.803, right? That's nice. 0.803. All right. And variances are still fixed. I'm going to just forego this part because you know what I mean to do here, right? Why we do the seeds so we can replicate the model just to save us a little time. This includes the internal and then covariates internal. I should do this internal constrained. I say constrained being equal. Constrained. So let's say constrained. So it means they're constrained to be equal. So it's internal and constrained to be equal with fixed variances. Let's go to model 5. So let's try something, one last thing here. Well, actually, do we have any interesting results? Let's take a look first. No forgetting everything. See what the results were. All right. So within classes, see, this is more what I expect. So this is really cool stuff. So what I expected was that males would have, oh, actually, no, interesting. Not what I expected. So males have higher, this has got to be female and male. So my guess is that this is a coding thing. So it's probably 1 is female and 0 is male. And you might think, well, why are you being, why are you saying that, right? Is that sexist? It's actually not, because I do a lot of research on on depression, and females are much more honest than males are. So it's actually males are the ones that are being less honest. So I'm thinking that I have that coding backwards. But anyway, so sex level 1 has higher depression than level 0, right? Right. So we see that is happening, and then here the rate of change is positive for that group. Okay. Let's take a look at the group 2. Group 2, you'll have a similar effect, but it shouldn't be the same. Oh, it is the same because I said that I didn't free them right yet. And then there's really no effect for school lunch. Because the data set is really large, you would never use an alpha of 0.10 here. If you say, well, it's significant. That's huge data set now. All right, so that's one thing that we did. Okay, and then how did it affect the impact here? What did it do here? So let's look at the odds ratios. So if let's say it's male. Okay, so male, since that's what I have it coded in my notes. So males would be 39, almost 40% as likely to be in group 1 as in group 2. And then actually now there's a significant effect for lunch. Oh, that's interesting. People who receive free or low cost lunch are 70% as likely to be in group 1 as in group 2. So this is group 2 would be people who tend to have free or low cost lunch and would tend to be male in this case. Do their groups remain the same? Do their groups remain the same? What it means. We don't have the same kind of means anymore now because they're really, is this like a residual that you're looking at, like residuals, right? So you can look at these intercept values. Yeah, so this one is much higher too. So and why I'm saying that is because when we were doing the regression without any predictors within the classes, we could just look at the mean values, right? Because there were no predictors. The mean value for intercept and slope, but now there are predictors. All we can look at is the residuals. Right. So all right, that's cool. So so this remains the same, basically. All right, let's look at the next one. All right, so the next logical thing to do would be to estimate these independently for the two groups. Okay? For the two groups. So let's do that. So, and I believe we'll do that. I don't want to get this wrong. I think I would do it. I think we'll find out. I think I'll do it here. Can't remember if it comes before or after the next set of code. My two classes, right? In the first class, I'm just going to leave this as is. I don't need to do anything with it. But in the second class, I'm going to ask this to be estimated independently. This should do it. So because I'm putting it in class 2, this should allow these effects to be estimated separately in group 2 from group 1. But I'm not so sure if this second line here goes before or after that. I guess we'll find out in a second, right? Let me try to run this. Get an error if it's done. I think people might be wrong, but it might be something else wrong, so I don't know. So let's try this here. But I think it's here actually. I think it's here. It's been a while since I've done this. I apologize. There you go. Yeah, that's right. All right. What do we have here? Now I'm going to make sure it ran it as I wanted it to run it. Okay. Let's just see if it's different. Okay, so we have 2.886. Yes, see, so you can see now it's different, right? This is really cool. Okay, so they're different. So it estimated them differently for the two groups. So in this group, we have a significant effect for sex, for the slope, intercept and the slope. And then here in group 2, we have a non-significant effect for sex and school lunch. Interesting. Okay, and then how about the differences? Sex is still the only thing that differentiates the two groups. I think in the last model, lunch did as well, right? So now we think, well, which model should I use? Well, this is where we go back to the BIC. Here's the BIC. Here it is. Control V. 8.1. So this model, look, it went up. So it fits worse, right? It fits worse. So I mean, that would tell me that just without going in further, this is the model I would pick because I'm not going to use a worse fitting model, even though in theory it seemed that, oh, relaxing these constraints would make everything better, right? It'll give me, I'll have done a better job, would have because you can see there's differences, right? But that's not enough for me to say that it works because the data really are telling me that it's not a better model than this one, right? Just because they say they're different doesn't mean they're statistically different between the two groups, right? So that's another issue right there that we have to check. So this is internal 3 fixed variance, right? So, and in terms of the other information we had, what do we have here? Let's get everything in there. We had entropy was nice. This was nice. So that entropy is 0.813 and the smallest class size was 14%. So nothing really bad here, 813 and 14%. 0.14, 0.813, I think, right? All right, so what's the bottom line here? I went through this whole process. So let's just recap everything from scratch. So I went through this whole process using Mplus, right? I went through this whole process to identify the number of classes, the number of latent classes of depression, or so the latent trajectories you can think of, because trajectory, you think about moving across time, right? Of depression. I started without having any predictor variables, and basically I fed a latent growth curve model into this this machine, if you think about it, right? that mixes things up and finds group. It's like I don't know. It's like I don't know if it's what kind of machine would do something like that would separate things. It's like one of those blood machines. When you work in a lab, right, and it separates the plasma, right? So I've seen those, they spin and stuff like that, right? This is like that, right? Excuse me. But we're separating the classes. We try to find classes that are maximally separated. We use things like multivariate Mahalanobis distance. It's this multivariate distance that separates the two, right? Classes, right? So we're trying to optimize that. And that's what the BIC is helping us do. And we're looking at that entropy statistic too, which ranges from 0 to 1, higher values meaning better separation. So we try to do that first without having any predictor variables. We looked at whether the model works better with fixed or freed variances. When this is estimated, the variance for the intercept and variance of slope is constrained to be equal across the different classes. Now remember, a latent class is just an unobserved class. Again, I could have done this to say, let's look at depression for females, let's look at depression for males. That would have been known grouping because that's a known class. We know who the females are, we know who the males are. I mean, you can debate that sociologically, but just if we assume that they're set, boom, boom, you can do that. You know who received free or low cost lunch and who didn't receive free or low cost lunch, right? So those are known classes. We're looking for latent, hidden classes that we're not aware of. So we went through this process. We tried to free the variances by class, and that didn't really work out that well. Excuse me. I mean, in this case, I didn't really go into it further. We could have looked at intercept by itself, slope by itself, and seen what, if anything, works. We didn't do that, but just assumed that this was good enough. Then we settled on a 2-class versus 3-class model where there's 2 separate classes, one that has really high depression at baseline, one has low depression. Neither of them changed that much since baseline, but they were clearly one group is high and one is low. Next thing we did was we added predictors where we used logistic regression to predict class membership, like who belongs to class 1 versus class 2 to males. And we had this issue. I'm not so sure about the coding, but what we found was the males were more likely being class 2, the high depression class, than females. And then lunch really didn't have any predictive ability. Next thing we did was we did a regression for the latent growth curve model, the intercept and trend within the classes, right? But we constrained them to be equal across the classes. So we said, okay, well, let's see what the effect of these variables is on the intercept and slope. And then we do our classification after the fact. So we did that and we found some interesting stuff. And then the third thing we did was we did the same as in the last model where we looked at the effect of sex and lunch on intercept and slope, but we modeled them separately for the 2 classes. And we saw that there were some differences. However, our BIC went up, and we're using the BIC as our way to determine the optimal number of classes. And this is telling us, well, it looks like this model doesn't fit that well. And again, there's just some judgment that has to be involved here too. But if those data aren't really telling me it, aren't supporting that, this is a good way to go, I just won't use it. I'll say, okay, well, we can leave the intercept and slope being regressed on sex and lunch and keep the effect to be the same across the 2 classes, right? But then we can profile our class membership. Just to be clear on something, that's what we do in regression anyway, right? In regression, if you look at the intercept and the slope term, you'll notice that they don't have like a separate I by them. They're fixed for everybody, right? So while your individual values and your predictor and your outcome will vary, but what won't vary is the effect or the intercept value and the slope value. The effect is the slope value. And basically that's what we said here too, right? Once we constrained this, see, like this didn't work out where we relaxed it and we measured it separately for class 2 from class 1. So we'd end up just doing this. So this is just telling us that the effect of sex and lunch on intercept and slope remains constant for everybody. Whoopie-doo, that's nothing different than what we do with regular regression analysis, right? So that's all we ended up doing. Pretty cool stuff. All right, so the next one, I'm going to do this with a categorical variable. Any questions for me? Well, let me shut this down first. Hold on. Let me shut down the recording and then I'll ask questions. Thank you for those of you who are just watching the recording.